All right, so this is lecture 6, starting again. So we're going to continue on a few basic things about elimination. And in particular, I want to talk a little bit today, and we will come back to this topic on some cases where elimination is going to fail. So let's take a very simple case of a 2x2 system of equations. You can actually, before you do anything, you can appreciate that this thing is not going to be something you can solve, because if you look at the second equation, it's 3 times. If you look at the matrix, right, the second row is 3 times the first row. All right, and if you look at the second column, it's really minus 2 times the first column. Right, so that matrix is really not invertible. And so if you actually try to do elimination of this matrix, and we're not going to repeat a simple case, so if you get rid of this 3 there by doing elimination, you get a system of equations where the second equation that results looks like 0 times y equal to 8. So you have 0 equal to some number, so you know this has no solution. Okay? So this case of having an equation that upon elimination looks of the form 0 equal to something that is not 0, it's very typical. So in that case, you cannot invert this matrix, and so we will see a few cases as we go along with square and, of course, non-square matrices. So in this particular case, where there is no solution, is not surprising. Again, you can see if you take the 2 equations correspond to 2 lines that they are parallel to each other. So obviously, these are the equations corresponding to the rows. So these equations don't meet. So there's no solution. But also, if you look at the columns are, in the same direction. Column 2 is minus 2 times column 1. So if you look at the plot of the columns, they are both of them in the same line. So there is no way you can take combination. You can take any vector on that line and somehow multiply with some constant and get this 1 and 11, okay? So geometrically, there is no solution to this problem. Okay, now if you somehow, you change the right-hand side and you make this 3, and you do elimination, the second equation becomes 0 equal to 0. So this system of equations has solutions, and it has more than one solution. Right, so we need to, in this case, we have infinite solutions, okay? So basically anything that is on this line, x minus 2y equal to 1, it is actually a solution. So anything on this line is a solution, or you can think, because the 2 column vectors are in the same orientation, any vector in that orientation, that will actually make it a correct solution. So we went to a simple case of 0 solutions to infinite solutions by manipulating this number there on the right-hand side. I don't remember what was there before, 11, and now we somehow have a 3. Okay, so we don't need this. So let me do some jumping. I'm going to go to slide 53. All right, so actually, not even 53, because I already mentioned this case. So let me go to slide 54 and go back to elimination. So when we do elimination to compute the solution of a linear systems of equations, one of the things that we said we do is we form this augmented matrix. We put B next to A, and then we start doing elimination to get an upper triangular matrix from A. And we do the same sort of operations on rows. We do the same operations on the vector B. And effectively, this system comes to be row equivalent to some new system of equations that I call here R and F, because I use the notation R instead of U, because we're actually going to do something extra to U today, okay? But let's say if you do any sort of linear operations on A and B, and if you get a system that involves a matrix R and F, these 2 systems have the same sort of solutions, okay? So if you solve AX equal to B or RX equal to F, It's the same thing because they are row equivalent. You just take linear combinations of rows. Nothing has changed. Okay, so what I want to do is I want to, as a preliminary step, because we will cover this topic hopefully in 1 or 2 lectures next week, I wanted to take a few examples that have different versions of how this matrix R is going to look at the end, and how the right-hand side F is going to look after you do elimination. So let's say you do elimination. This is a very general form that you will expect to get. So can you tell me, so this square at the bottom is all zeros. Can you guess from where all these zeros came from? So you start doing eliminations, right? You do, you know, the elimination process we did in the last lecture. From where are all these zeros? So some things disappeared. You remember some rows are linear combinations of the previous rows. So when you do eliminations, what happens to those rows? So when you do linear, when you do elimination and some rows are linear combinations of other rows, what happens to those rows? They disappear, they become zeros. But obviously here I'm implying that you're going to do some row exchanges as well, right? Because you don't know which row is a combination of what. So if somewhere you have a zero pivot, you do some row exchange. But at the end of the day, with row exchanges, you will get anything that is a linear combination of other rows disappears, and you get all zeros that you see here. But notice, if you do the same operations on the right-hand side to the vector B, you may or you may not get zeros on the vector B. Right? So we did whatever operations we do on the matrix, we do also on the right-hand side, and it may turn out that FR plus 1 to FM may come to be 0 or may come to be anything else. So if they're not 0, what can we conclude? So if FR plus 1 to FM is not 0, what can we conclude? That the system of equations AX equal to B has no solutions. Okay? Obviously here R, even though formally I will redefine this, is the number of independent rows, and we define R to be the rank of the matrix. Okay, so the row elimination will actually identify for us what the rank of this matrix is. And as a result of the row elimination, this triangular everything there is also 0. Okay, so what I want to do is very preliminarily, without doing fancy details, just elementary things, because you have to do the homework, I want to do a few examples so you can actually see how this matrix may look like in a few basic examples. So let me, I'm going to go directly to the example. I don't have time to read and see what's going on here. So let's take this 3x3 system of equations that you see here, okay? And we want to solve it. So obviously you immediately see that this matrix is not invertible. Can somebody see immediately why this matrix is not invertible? I mean, if you look at the rows, look at row 3 and row 1. What can you tell me? Row 3 is what? Row 3 is 2 times what? No, actually wrong. No, wrong. Okay. Wrong. All right. Is this matrix invertible? I don't know. You have to start guessing here. You have to help me. Well, actually, immediately I can see it. I can see it. Forget the rows. Look at the columns. I already saw a pattern there. If you take column 1 minus column 2, what do you get? Column 1 minus column 2. You get what? Column 3. And so obviously the columns are not independent, which means the rows are not independent. So this matrix most probably has rank 2. All right, so it's not invertible. And indeed, if you do elimination on this problem, this is what you get, right? You get 2 independent rows, and I'm not going to repeat elimination. You will get rid of that 2, you will get rid of the 6, and then you will get rid of that 2 in the third row, second column. And then what you get is you get your 0 row, all right, that we have seen here on the bottom. And when you do the same operations of elimination on the vector B, so you get a 12. And looking at the last row, what can we conclude based on what we said? That this system of equations has what? No solution. Okay? All right. So let me do another case. Again, we don't need to generalize. Let's look at this example that sounds a little bit more interesting. This example has 4 equations. Actually, so this is the first time we do something that is non-squared. All right, so it has 4 equations. So it is what we call overdetermined. Give more equations, we only have 3 unknowns. Okay, so this can be trouble. I mean, in general, we will address this type of problems in this course using more sophisticated techniques from linear algebra. But right now, based on what we know, this problem can be trouble. 4 equations, 3 unknowns, okay? So the only thing we know is how to do elimination. So if we put things together and we do elimination, this is what we get. And I'm only doing eliminations up to getting that upper triangular matrix U. So what happened to the last equation? I get 0 equal to 0. And how many non-zero pivots I have in this problem? 3. So the rank of this matrix is 3. It's invertible, obviously, so the fact that I had 4 equations is not a big deal because the 4th row is really a linear combination, obviously, of the other 3 rows, okay? And again, you don't have to guess it. If you do elimination, automatically that comes out, and because you have a 0 equal to 0 there, this is what we call a consistent system of equations, and so we have a unique solution to the system of equations. Let me see if there is another example. So here's another example where the equations that I have is 3 by 4, all right? So this system is underdetermined, all right? I have more unknowns than equations. I don't want you to be scared and say, how can I solve this? Yeah, we will learn how to do these things in this course, but here we have 4 unknowns, x1, x2, x3, x4, and we only have 3 equations. This here is the right-hand side. So what you do is you do elimination, and you look at this. First, the good news is 0 equal to 0, which means there are solutions. How many solutions in this problem do you think we have? Because you have to do this type of problem in the homework. How many solutions do we have for this problem? 1, 2, 3, how many? Infinite, okay? And so when you look at this problem, you notice the pivot here 3 is non-zero. This is in the diagonal also a non-zero pivot. So the pivot variables are x1 and x2. The other variables, x3 and x4, are what we call free variables. Free variables. And free variables means to find a solution to this system of equations, you can go and set x3 equal to 1 and x4 equal to 0. So you can uniquely then identify x1 and x2. Or next, you can go and set x4 equal to 1, x3 equal to 0, and uniquely identify x1 and x2. And so then, we will see, actually, hopefully today, how we can take combinations of these solutions to come up with a general solution of the system. But bottom line for now, this problem has infinite solutions. Let me see, because I have to do some jumping today. So not jumping, we go to slide 59. So let's use this LU factorization and take it one step further so we can actually compute the inverse of a matrix using what's called the Gauss-Jordan elimination. And I am going to do a lot of jumping. There is a lot of blah blah in the notes that you can read. And I'm going to go in what we need. And what we need is this slide. And only. So I want to find the inverse of a matrix A. And I'm working now with rectangular matrices. Simple things, okay? So we're working with rectangular matrices. And I want to find the inverse of a matrix A. Remember, we know how to use elimination and solve AX equal B by forming the augmented matrix A and B. Now, to compute the inverse, don't you think with me it's equivalent? Let's say if I want to compute the inverse of a 3 by 3 matrix, don't you think it's the same as solving 3 systems of linear equations where the right-hand side is 1, 0, 0, then 0, 1, 0, and 0, 0, 1? Right? So how about if I just put all of them together and form an augmented matrix that looks A and the identity matrix I? Okay? So we form an augmented matrix A and I, all right? We want to invert A. And here's what we're going to do. We're going to apply these elimination matrices that we learned from lecture 4, okay? And we're going to apply sort of, combinations of rows, right? That's what elimination is, in a way that somehow multiplying from the left the matrix A with the matrix C is going to make the matrix A the identity matrix. Not just the upper triangular U, but once I get U, I'm going to try to make the diagonals 1 and get rid of everything above the diagonal. So the matrix becomes an identity matrix. And I can do this with row combinations, okay? And I'll show you an example shortly. So we're going to find a product of elimination matrices so that EA becomes the identity matrix. And obviously then, if I apply the same operations, row operations on I is going to become this the product of the elementary matrices E. All right? Now, do you agree from the fact that I see here E times A equal to I, so really E is what? Is the inverse of A. And if E is the inverse of A, immediately when I do the same operations that I did on A on the identity matrix, what do I get there? I immediately get the inverse of the matrix. So basically the Gauss-Jordan elimination is do what you know up to now, okay? Do it also on an augmented matrix that involves A and I, but don't stop where the LU factorization stops. Continue, make the diagonal elements 1, and then put zeros above the diagonal. So make the whole matrix basically the identity matrix. That's what Gauss-Jordan does. Now, in the LU factorization, we don't need to do this, but to find the inverse of a matrix, you actually need to do this type of thing. So let me see if there is an example. And I'm going to do, let's start with some trivial examples. So let's say that I give you a matrix A that is 1, 2, 3, and 7. So we're going to form the augmented matrix. This is the augmented matrix. I put the identity matrix there, all right? So elimination is going to proceed. We're going to get rid of this 2. So we're going to remove from row 2 times row 1. You agree? And I'm going to do the same operations on the row 2 of the identity matrix. So here, for example, if you subtract 2 times row 1, you're going to get a -2. And there you will get a 1. And what have I done to go from here to, we don't stop, okay? The way that you see here is, you say this is my U, right? Stop. No, we don't stop. We will do one step further. First, the good news is that the diagonal elements are 1, okay? That's by accident, by choosing an easy problem, okay? And so what we would need to do is get rid of that 3 above the diagonal. So tell me, what row operation are you going to do to get rid of that 3? You're going to subtract how many multiples of row 2 from row 1 to get rid of that 3? 3, all right? So let's try, for example, with the third column. I'm going to have 1 and I'm going to subtract, where are we? So you're going to subtract 3 times, all right? So you can see you're going to get a 7 there, okay? And what is this new matrix that appears where the identity goes? What matrix is that now? Is the inverse matrix of A, and you can actually check that if you multiply this matrix with A, if you don't trust me, and you should not, because when I type and copy these formulas, who knows what I copy and I write down? Because every time I read, I realize there's another typo here and there, so I rely on you to correct me. All right, don't assume, and spend 10 hours, say, but this doesn't work. You check it, and then you send me an email and say, sorry, it doesn't work, it's wrong. Okay? Trust but verify. All right, and let's do let me see if there is a 3 by, okay, here is a 3 by 3 example. Very simple, exactly as before. If the matrix A looks like this, so what you will do is you will put the identity matrix to define the augmented matrix. And just let's see at the steps. To go from here to there, what is the first step we do? That is different from before. To go from the left to the right, look at the matrix A. What have I done? Row exchange. All right, we do a row exchange because the first pivot there is 0, which is not good. So we put this as row 2. And then the only thing we need to do is eliminate that 4. All right, we eliminate it. Then we look here. So we have to eliminate now what? The -3. We did. And then you remember with Gauss, with the LU factorization, you will stop there and say, there is the U matrix, done. But now we don't stop there. First, that 2 has to become 1. So we're going to divide the last row by 1. I mean, by 2. So 3 halves minus 2, 1/2. And then we're going to have to get rid of 2 and 3. And how do you get rid of 2 and 3? You're going to have to subtract from rows 2 and 3, 2 times and 3 times row 3. And when you're done, all right, what is this weird matrix? That's the inverse of the original matrix A, and so we're done. Okay, so this is, what slide it says? Slide 70. Okay, so I'm going to jump a lot now, and I'm going to go to, no. What did I press? Okay, we're going to go to slide 82. No, that's not good. All right, so I want to look a little bit ahead because you have a homework due, and I want to be sure that I covered some elementary ideas, from that you need to do the last problem. I mean, literally, lots of the things we do are trivial, but we have, if we sort of give everything, the whole lecture of linear algebra in one lecture, you're not going to learn anything. And then at the end of the day, when we start using concepts in differential equations, you will not be able to follow. So I don't feel bad going slowly on this, okay? In some sense, it's boring for me, and I hope it's not boring for you, okay? So I'm going to try to bring things to some excitement by doing things that you have not seen in other linear algebra courses. And maybe what I will do now, you haven't seen it in this form, okay? Even though in principle, it's all about nothing, because it's too basic. So what we would like to do is, so we started trying to solve AX equal to B for square matrices, more or less. So I would like to actually address the general problem. If I give you a matrix A and a vector B, can you find me the solutions of AX equal to B? And before we solve AX equal to B, I want to address the problem, can you solve AX equal to 0? And AX equal to 0 defines which space? How do we call it? The null space. So we need to find basically the solution the vectors that are solutions to the null space. And in principle, we need to find the basis of the null space, right? We need to find the basis of the null space. Okay, so I'm going to give you a summary first. This is from a table from Professor Strang's book. And then we will expand on the different items on this summary to see that things are not very complicated. So the definition of the null space, right, is all the x's for which ax equal to 0. And of course, the most trivial solution of the null space is x equal to 0. So in principle, we're looking for things that are non-zero solutions to the null space problem. So the important thing is, since we are going to be doing elimination and row operations, the good news are when you do row operations and you bring the matrix A to an upper triangular matrix U, that's our LU factorization, and then basically to this row echelon form that we will discuss today, similar to what we did with the Gauss-Jordan form, these operations in rows do not change the solutions to the null space. Because what is, if you think about it, right, there is nothing, if you change the rows, the x's that give you ax equal to 0 will also give you ux equal to 0 and rx equal to 0. Because how do you get u? You multiply a with some matrix E. So if I have ax equal to 0, E times a times x equal to 0. And if I do further operations, r times x equal to 0. Nothing changes. Okay? So that's good, which means maybe all these operations will be very useful to identify the solutions to the null space. So we're going to bring the matrix A to what is called the reduced row echelon form. Okay? This is the zigzag form that we saw before for some of the rectangular matrices, because up to now, the trivial problems we discussed, the pivots are always in the diagonal. That may not be the case. So the pivots may not be in the diagonal. That's how you're going to get this form. We're going to do the same idea that we did for Gauss-Jordan form. We're going to make the pivots equal to 1, and we will have zeros above the pivots. When we do this row echelon form, there will be some columns that are what we call free columns. They have no pivots on them. And those are essential basically to define the solution to the null space. And those solutions are called special solutions. So for the columns where you don't have any pivots, you can actually identify the special solutions by setting each of them one at a time equal to 1 and the rest equal to 0. We will do examples, right? So I'm going to come back to this. But so there will be columns that basically have no pivots on them. And those columns define the free variables. And the free variables basically will give us the solution to the null space problem. OK? So the number of pivots, we already have seen this. They define the rank of the matrix. And the remaining number n minus r is the number of free variables or free columns. And n minus r is going to actually be the dimension of what space? I remember I had a slide in the past that I threw at you that concept. So R is the rank, and we said we're going to have these columns that have no pivots on them, that identify the null space. So the rank of the dimension of the null space is going to be how much? N minus R. I mean, you can guess it. We will come back to it, OK? The dimension is going to be N minus R. Now, it says in the last statement that if you have a matrix that has m less than n, the null space has non-zero solutions. Can you tell me why is that the case? Remember, my matrix A is m times n. So if m is less than n, why the null space has non-zero solutions? Give me an argument. If m is less than n. What is the maximum rank this matrix can have? If I have m rows right? What is the maximum rank that matrix can have? And remember, from the elementary way we have seen it in the past, and rank is the number of independent rows. So what's the maximum number of independent rows? M. So how many free variables will we have then? There. So how many free variables will we have? N is bigger than M, right? So N minus R is going to be these free columns that define the free variables, and those will identify the dimensionality of the null space. Okay, I gave you the summary before I gave you the details, so let's look at the details. So let's take this weird matrix. So no more rectangular matrix, not square matrices, right? So we're going to take a matrix that is 3 by 4, okay? And our homework problem is to find the null space and also to find the basis basically for the null space. What is the general type of solution X that we get for AX equal to 0? All right. So the first thing I'm going to do is I'm going to start doing elimination. So I'm going to go from here to there. Can you look at interesting patterns on this matrix? Look at row 3. What can you tell me about row 3? Is the sum of which rows? Can you see that? Row 3 is what? Is row 1 plus row 2. So it's not, so can everybody see this? Right? Am I correct there? 6 plus 2, 8, 2 plus 8, 10, etc. So anyways, we will identify this when we do the elimination. So if you start the elimination process, this is what you get. So are you surprised that you get 2 and 4 there and 2 and 4 there? No, because you know the third row obviously it's dependent. It's the sum of the other 2 rows. So this is what we get. Okay. Let me just. So this is my matrix U, right? This is the upper triangular matrix. So if I do one more elimination step, I will get rid of that 2 on row 3, column 3, and this is what I get. So this is my upper triangular matrix, but actually because I will not call it anymore upper triangular matrix because my matrices here are not square. So this is the row echelon form, all right? This is the zigzag form that we get. And you notice in the second row, what element defines the pivot? You remember when we discussed about pivots for square matrices, the pivots were always in the diagonal. Here, the pivot is where? In the second row. It's not in the diagonal. So the first non-zero element in row 2 is the element basically 8, 2, 3. Okay? So, so when you look at this, okay, the pivot columns identify basically, all right? So here what I have, you know, I have 2 pivot columns. They identify basically how many independent columns I have and how many independent rows I have, and the number of those is 2. Okay? So effectively, you can actually think of 1, 0, 0 and 2, 2, 0. You know what they define? In terms of spaces. This is where I have the pivots. So in terms of spaces, can you guess somehow those will be the basis for what space? The column space. Okay? So this other 2, the other 2 columns that you see, I call them, free columns, all right? And they will identify the solution to the null space. Now, none of this is clear yet. I mean, I see we got this weird matrix that I still call it U here. The pivot element is not in the diagonal, so it looks like this. So interesting, but, you know, things look weird at this point. All right. So the number of pivots here defines the rank of the matrix, all right? And as we said, it's 2. Now, do you agree with me? Okay, so let me just go one step back. Do you agree with me, because I did only linear combinations of rows, that if I want to find the solution to AX equals 0 is the same as finding the solution to UX equal to 0? Right? The solution of the null space hasn't changed because I did combinations of rows. So to solve AX equal to 0 is the same as solving UX equal to 0. So what I'm going to do is I'm going to give you first the trivial way of computing the solutions to the null space, and then I give you sort of later on a more rigorous mathematical form that automatically tells you what the solution of the null space is without you having to do any algebra. So right now what I'm going to do is I'm going to give you what most probably you already know, and then we will try to formally write some equations to identify that. So, so this first column is variable x1, the second is x2, x3, and x4. And as I said, the variable x1 and x3, okay, are the pivot variables, all right? And the free variables is variable x2 and x4. And I call pivot variables the ones that correspond to the columns that have non-zero pivots. So that's column 1, and that's column 3. It happens that here is not column 2, it's column 3. So the free columns here the pivot columns are column 1 and column 3. So to identify the solution to UX equal to 0, you have to do the following. Take the variables that correspond to the free variables, x2 and x4, and set each of these variables one at a time equal to 1 and the other equal to 0. So we're going to set x2 equal to 1 and x4 equal to 0. And then we're going to set x2 equal to 0 and x4 equal to 1. And once we do that, we're going to solve for which variables? If you know what the variable x2 and x4 is, can you solve for me? If I give you ax equal b, can you solve and tell me what x1 and x3 is? We're not going to do it on this problem because we're interested in the solutions of the null space, but you can. Right? Because you eliminated the fact that there were many solutions by setting the x2 and x4 to some given values. So I am going to set x2 equal to 1 and x4 equal to 0. I am going to solve ax equal to 0. All right? So for example, if you take the second row, this will be 2 times x3 plus 4 times x4 equal to 0. So if x4 equal to 0, x3 is equal to 0. And then if you take the first row, ux equal to 0, you're going to have x1 plus 2x2 plus 2x3 plus 2x4 equal to 0, right, which is here. And if x2 is equal to 1, so this is minus 2, and this is 0, then x1 is minus 2. Okay? So one solution to ax equal to 0 is given by this vector. Minus 2, 1, 0, 0. Where did this 1 come from? By setting one of the free variables equal to, where did we get that 1? We set one of the free variables, which is variable x2, equal to 1, and the other variable that is variable 4 equal to what? To 0. And we solve for the rest. Okay? And we can do the same thing with setting variable x4 equal to 1, all right, and x2 equal to 0, and solve for x1 and x3. And that gives me another solution that you see here. And these two solutions are basically the basis of the null space. So the null space is the plane that you see up there. It's a combination of those two vectors. All right? We haven't done, all the fancy details that I would like, to do in 3 hours. But in principle, what we did is, by having this row echelon form, we managed to identify the pivot columns, okay, x1 and x3, and then the free columns that correspond to variables x2 and x4. So the null space is defined by this spatial solution, spatial vectors, where one of the free variables is set to 1 and the other to 0. Here is again 1 is to 1, the other one is to 0. And then the rest of the pivot variables are computed by solving AX equal to 0 uniquely. Okay? And what we get is, we get a null space here that is a plane defined by these two vectors. So any vector that is a combination of these two vectors, it's a solution of the null space. And actually, you can, without doing any algebra, can you look at, let's look at this thing here. I say that minus 2, 1, 0, 0 is a solution to the null space. Let's go back. Remember, minus 2, 1, 0, 0. Okay? Look at this and tell me, why is minus 2, 1, 0, 0? Why is that a solution to the null space? This was my original A. Actually, was that the original A? Yes. So, why is minus 2, 1, 0, 0 solution? Look at that. Because column 2 is what? Look at that matrix. Column 2, the solution to the null space, right? When you take AX, what is AX? Is a combination of the columns. So you remember, the solution to the null space that we got was minus 2, 1, 0. So we take minus 2, the first column, plus the second column, and then it says that is 0. Is that 0? So effectively, the null space identifies for us what? That the second column is 2 times the first column. It identifies what the dependencies between the columns. So when I say these are the pivot columns, what columns are those? Those are the independent columns that you can extract. The rest of the columns are linear combination of the pivot columns. And the solutions to the null space tells you nothing else but what are the linear combinations that define the free columns in terms of the pivot columns. All right? So some columns are independent. That's it. They define, my solution space, the column space. The other columns are linear combinations of the pivot columns, and the null space solution tells you which combinations are those. Makes a little bit of sense? Okay? So when you get the solutions, what you need to do is you have to go back and look, and you say, don't believe it, let me verify what's going on, okay? All right, so let me make it very fancy for you and give you an automatic way to calculate the null space without having to set this to 1 and this to 0, but somehow automatically. And we have to do all of the above in less than 5 minutes. So this is the matrix U that we had, okay? So I'm doing one further. I multiply with another elementary matrix to get this form. Can you tell me what exactly have I done to go from here to there? Tell me the linear operations that you see that we have done there. So the first thing what I see there is 1. So how do I get 1 on that pivot column? To get 1, what have I done? I took that row, the pivot row, and divided by 2. And then what else have I done? Above the ones that correspond to the pivot columns, I have to put zeros. So I basically subtract, once you put this 1 there, I subtracted how many times row 2 from row 1? How many times I subtracted row 2 from row 1 to get a 0? You remember here there was 2, and then I have 1 there. So I'm going to have to subtract 2 times row 2 from row 1. Okay? So to get this row echelon form, we have done 2 major things. We put 1s in the pivot elements. We put 1s. And above the pivot elements, what do we do? Above the pivot elements, 0. Okay? And of course, everything else, these vectors, these three vectors, the second vector and the fourth, have to be adjusted. I mean, when you do raw operations, whatever it comes, you put it there, okay? So we get 2, 0, 0, and minus 2, 2, 0. So notice that when you look at the pivot columns, so I have 2 pivot columns and 2 pivot variables, x1 and x3. Notice that what is hidden there, looking at the pivot columns alone, is the identity matrix I. All right? So effectively, if I take this row echelon form and I change the order of variables, so if I said x1 and x3 are pivot variables. So how about if I put those to be the first 2, and then I put x2 and x4 to be the last 2? Would you agree with me that this matrix will become an identity matrix? You see the identity matrix there? Times some matrix F. And I call it F because it's identified by the 3 variables. And then I have a 0 and a 0 there. And can you tell me what's the dimension of the matrix I? Because I defines my independent columns and independent rows. So in a general matrix, what's the dimension of the matrix I? What is the number of independent rows and columns in a matrix? In general, what is the name we use for it? What's the number of independent rows? How do we call that? The rank of the matrix, which we denote as R. So this I is of rank R by R. I mean, it's a matrix R by R, an identity matrix. In our example, it's 2 by 2. So F is a matrix. In our case, it's 2 by 2 because I have R is equal to 2, and I have how many free variables? I have 2, okay? So in general, F is a matrix R times n minus R, okay? And what is the zeros there? What's the dimension of the 0 vectors? How do we get zeros? So if I have a matrix, let's say m by n, how did the zeros come? I started with m rows, and I told you that everything there is R. The rows there in I and F is R. So this has to be m minus R. What is m minus R? So when you do elimination, right, you get rid of the rows that depend on the other rows. So what you left is what? The zeros. You remember how many zeros you're going to have? M minus R in general. Okay? So doing this row echelon process, elimination process, you can, and rearranging the variables so that the pivot variables come first and the free variables come second, okay? This matrix case that takes the form IF00. And let me just tell you immediately, if this is the case, let me just tell you what the solution to the null space problem is right away without doing any calculations. So remember, we want to find the solution to AX equal to 0. And because we produce this matrix by doing raw operations, we want to find the X such that Rx equal to 0. And I'm claiming that this vector is the solution to Rx equal to 0. So what I want you to do is take this matrix, multiply it by that, and tell me if you get 0. Take this matrix in general, it's not a particular case, multiply this by this, and tell me if you get 0. So from the top block matrices, what will you get? I times minus F and F times I. What does that give you? The 0 matrix. And what do you get from the bottom? 0 times minus F and 0 times I, you get 0. So basically, the solution to the null space problem is minus F I. So effectively, you look at the matrix that you had identified for the free variables, and you copy these numbers, but with a minus sign. And what do you do on I? You put the identity matrix. And you know what? Those two vectors that you see there I know you're not going to believe me. They are exactly actually the null space bases that we identified before manually. Where what did we do? We set one of the free variables equal to 1, and then the other one equal to 0, and we computed the pivot variables. Then we set x4 equal to 1, and x2 equal to 0, and we identify x1 and x3, and there is the two pivot variables. The only thing that I have done differently in writing this equation is the following. I have rearranged the number of variables. So now I don't have x1, x2, x3, x4. I have x1, x3, because x1 and x3 together are what? They're the pivot variables, so then I put x2 and x4. So effectively, if you do this row echelon form, effectively, by identifying this minus f matrix, all right? Can you see here my minus f? It consists of this 2, 0, and minus 2, 2. That's what that's my f matrix there, all right? 2, 0, and minus 2, 2. So you know what? Those 2 zeros and minus 2, 2, they tell me what combinations of the column 1 and column 3 that are the independent columns, they give me actually the other two dependent columns. Immediately, you don't have to do any algebra. The only thing you have to do is, actually, you know what? The only thing you have to do is change the sign, right? To get the solution in the null space, put a minus there. So whatever elements you had, plug in the f minus 2 and 0, and 2 and minus 2, and put the identity matrix there, and you are done. All right. I had 2 slides left. I noticed 11:23 to tell you how to solve AX equal to B, and I have an automatic way to tell you. So actually, we have 2 minutes. If nobody comes, let me just tell you. If you do AX equal to B, and you apply the same operations, this row echelon form that we did here, notice that these pivot variables are multiplied. They include this identity matrix. So if you want to get a particular solution to AX equal to B, you don't have to do anything because the solution is directly on the vector B on the right-hand side. Because on the left, you multiply with the identity matrix. Okay, so let me leave there before anybody starts throwing us out. So there are 2 extra slides and an example that is all that you need to do the homework problem that is a simple application of what I showed you today. Okay, so have a good weekend, and I'll see you on Monday.